Hey everyone, Russ here. Today we're going to talk about Guy Lussac's law relating temperature to pressure. Now, in Charles's law, we saw how temperature can affect the volume of a gas if the container is allowed to expand, like a balloon, a soft container, if you will. What about in a hard container or a rigid container, like a bottle of hairspray, like a metal bottle of hairspray, or any kind of metallic object that's filled with gas? If you increase the temperature of a gas in a non-expandable container, the pressure will go up. If you decrease the temperature of a gas in a non-expandable container, the pressure will go down. When you heat up a gas in a non-expandable container, the pressure of the gas will go up, or the pressure in the container will go up. When you cool down a gas in a non-expandable container, the pressure inside the container will go down. Now this has everything to do with the kinetic energy of the gas. The more energy you pump into a system, a gas for example, the more that gas is going to fly around more rapidly, can contact the sides of the container more often, and increase pressure. That's how it's going to work. If you cool down that gas, it's taking away kinetic energy from the gas, causing it to hit the sides of the container less often and with less force. So that's what's happening when you increase or decrease pressure. Okay? Guy Lussac's law looks just like Charles's law, except for instead of using volume, we're using pressure. But the calculations are essentially the same. So here's a calculation. It's always good just to jump into calculations and start working them out because, that's what you're going to do in an exam anyway for the most part. A gas has a pressure of 2.0 atmospheres at 18 degrees Celsius. What is the new pressure when the temperature is 62 degrees Celsius? Okay. Pi equals 2.0 atm or atmospheres. Ti equals 18 degrees Celsius plus 273. It's a gas law. So you may as well put everything in the Kelvin right away. And 18 plus 273, 291. PF equals, well, that's what we don't know. We need to figure that out. TF, however, we know is 62. 62 plus 273, 335 Kelvin. Okay, we know that Boyle's law, we know that Guy Lussac's law is Pi over Ti equals Pf over Tf. Do a quick rearrangement. Pf equals Pi Tf all over Ti. Plug in some numbers. 2.0 atmospheres multiplied by Tf, which is 335 Kelvin. All that will be divided by Ti, which is 291. Temperature units cancel, leaving us in a volume for pressure, which is atmosphere. Bust out your calculator. 2 multiplied by 335, divide that by 291, equals 2.3 atmospheres. So that's how much the pressure will go up in this system. Now check it for logic again. We're at 18 degrees Celsius. We're going to 62 degrees Celsius. So the pressure should go up because the temperature is going up. So the logic works. The pressure did go up by 0.3 atmospheres. So that's good. Logic holds true. A gas has a pressure of 645 torr. Okay. Pi equals 645 torr. Torr is another unit for pressure. Essentially the same as millimeters of mercury. Ti equals 128 degrees Celsius plus 273. Just convert it right into Kelvin. Don't hesitate because you're going to need to anyway. 401 Kelvin. Pf equals 824 torr. Tf equals, well, that's the question now, isn't it? And it also says in degrees Celsius. Let's be very careful there. A lot of times in questions like this, they will ask you to report your final temperature in degrees Celsius. And if you don't, you lose points, so be mindful of that. So Ti over Pi equals Tf over Pf. Tf equals Ti Pf all over Pi. Ti is 401 Kelvin. Pf is 824 torr. All of that now is divided by Pi, which is 645 torr. Units for pressure cancel, leaving you in a temperature unit, which is good. 401 multiplied by 824 equals, divide that by 645. Calculator gives me 512 Kelvin. 512 Kelvin minus 273 equals 239 degrees Celsius. So let's check that for logic. The pressure, went up, so therefore the temperature must have gone up. I started at 128 and I ended up at 239. So that makes sense. The logic holds true. Okay? Now that's the end of the Guy Lussac portion. If you found this video helpful, please go ahead and slap the like button, leave a comment, and maybe consider subscribing to my YouTube channel. And with that, I want to wish you all good luck and good chemistry. We'll see you soon.